Yes, welcome back to my YouTube channel. This is K. Priya of 5th semester, studying in Sri Venkateshwara College of Engineering. And today my topic is about deterministic finite automata. Now let us see the introduction about deterministic finite automata. Deterministic finite automata is also known as DFA, is a fundamental concept in computer science and formal language theory, playing a crucial role in understanding and analyzing behavior of certain types of systems. Developed as a mathematical model, a TFA represents a simplified computational device with finite states, transitions, and a well-defined set of rules. This essay dwells into the key components, characteristics, and applications of deterministic finite automata, shedding light on its significance in the realm of computation. The picture which is shown here is the example of DFA, that is deterministic finite automata. Now let us see the components of a DFA. A deterministic finite automation consists of several essential components that collectively define its structure and operation. There are states, alphabet, transition function, initial state, and accepting states. Now let's see in detail. Alphabet. The alphabet is a finite set of symbols or inputs that the DFA can read. These symbols serve as the language with which the automation interacts, influencing its state transitions and states. The DFA comprises a finite set of states, each representing a distinct configuration or condition of the system. These states encapsulate the possible state of computation during the processing of input. The transition function detects how the DFA moves from one state to another based on the current state and the input symbol. In the deterministic automation, this function is deterministic, meaning there is a unique transition for each combination of state and input symbol. Initial state. The initial state marks the starting point of a computation. It is the state from which the DFA commences processing the input string. Accepting state. The accepting states from a set of states or a subset of states that signify successful completion of recognition of the input string. If the DFA reaches any of these states, the input string is accepted, otherwise it is rejected. Now let's see the operation of a DFA. The operation of a DFA is defined by its deterministic nature. Starting from the initial state, the automation reads symbol from the input string one at a time. The transition functions guide the DFA, determining the next state based on the current state and the input symbol. This process continues until the entire input string is processed. If the final state is one of the accepting states, the input string is accepted. Otherwise, it is rejected. The deterministic nature of DFS ensures predictability and well-defined behavior during computation. At any point in the process, there is only one possible next state, simplifying the analysis and understanding of the automation's operation. And this is the basic other example of DFA, that is deterministic finite automata. Let us see some advantages and disadvantages of DFA. DFS are one of the most practical models of computation since there is a trivial linear time, constant space, online algorithm to stimulate a DFA on a stream of input. Also, there are efficient algorithms to find a DFA recognizing the complement of the language recognized by the given DFA. The union or intersection of the languages recognized by two given DFAs. Because DFAs can be reduced to a canonical form, that is minimal DFAs, there are also efficient algorithms to determine, example, whether a DFA accepts the string, there is emptiness problem, whether DFA accepts the string, that is universality problem, whether two DFAs recognize the same language, that is equality problem, whether the language recognized by a DFA is included in the language recognized by a second DFA, that is inclusion problem. The DFA with a minimum number of states for a particular regular language, that is minimization problem. DFS are equivalent in computing power to non-deterministic finite automata, that is NFAs. This is because firstly any DFA is also an NFA. So an NFA can do what a DFA can do. Also, given an NFA using the power set construction, one can build a DFA that recognizes the same languages as the NFA. Although the DFA can have exponentially larger number of states than the NFA, however, even though NFAs are computationally equal to DFAs, the above mentioned problems are not necessarily solved efficiently also for NFAs. The non-universality problem for NFS is PSPAC complete. Since there are many small NFAs with shortest rejecting world in exponential size, a DFA is universal if and only if all states are finite states. But this does not hold for NFS. The equality, inclusion, and minimization problem are also PS-based complete since they require forming the complement of a NFS which results in exponential blow up of size. On the other hand, finite state automata are of strictly limited power in the languages. They can recognize many simple languages, including any problem that requires more than constant space to solve. Cannot be recognized by a DF. The classic example of simply described language that no DF can recognize is bracket of Dyke language. That is, the language that consists of properly paired brackets such as a word, an example bracket. Intuitively, no DFA can recognize the Dyke language because DFAs are not capable of counting. A DFA like automation needs to have a state to represent any possible number of currently open parentheses, meaning it would need an unbounded number of states. Another simple example is the language consisting of strings of the form a power n, b power n of some finite but arbitrary number of followed by an equal number of b's. Now let us see some applications of DFAs. Deterministic finite automata find applications in various fields, including but not limited to lexicon analysis. DFAs are widely used in the design of lexicon analyzers for compilers. They help identify and categorize tokens in programming languages based on pattern defined by regular expressions. String matching. DFA are employed in string matching algorithms, allowing efficient searching for specific patterns or substrings within text. Natural language processing. DFAs are applied in natural language processing tasks such as text processing and language recognition, where they can be used to define grammars and patterns. Network protocol analysis. DFAs are utilized in network protocol analysis to model and analyze the behavior of communication protocols, aiding in the detection of anomalies or security threats. This is another example of DFA. And let us see the conclusion about today's topic, that is deterministic finite automata. So, deterministic finite automata stands as a cornerstone in the study of formal languages and computation. Their simplicity, determinism, and well-defined structure make them invaluable in various computational applications, whether used in lexical analysis, string matching, network protocol analysis, or natural language processing. DFAs provide a solid foundation for understanding and solving problems in diverse domains. As technology continues to advance, the principle embodied by DFAs remain relevant and foundational, underscoring their enduring significance in the world of computer science. Thank you for watching this video. If you like this video, please like, share and subscribe to my channel.